Okay, let's do a couple more and then we'll call it good for this. So we're working on the chain rule. And we want to go ahead and find an equation for the line that is tangent to this function at that point. And so that's what our instructions are telling us to do. And so to find the tangent line, we actually need to take the derivative. If you are not very comfy with taking the derivative using the chain rule quite yet, I would recommend you at least follow along. But know that you can always take f and split it up into tangent x, which means that you can employ the product rule. You still have to take the derivative of the tangent. Sorry, you're just not going to get by that. But that's not bad. Okay, so we've identified the inner product, or the inner function is tangent, the outer function is square, and so we take the derivative of the outer, which is 2 tangent x to the first, and so there's nothing left, times the derivative of what's inside. And the derivative of tangent is secant squared x. And so there's our function, or there's our derivative. Now we need our derivative at that point because that's the slope at that of the tangent line at that point. All right, so f prime of pi over 4 is equal to 2 tangent pi over 4 secant squared pi over 4. Now, as far as tangents and secants and cosecants and cotangents go, I'm not very up to it. Shh, don't tell anybody. However, I can always put these back into sines and cosines, which I'm really good at. Okay, so let's go ahead and do that. Now, tangent is sine over cosine. Sine and cosine are the same at pi over 4. They're both square root of 2 over 2. And so what I'm really doing is I'm taking some number, square root of 2 over 2, and dividing it by itself, the square root of 2 over 2. Anything divided by itself is 1, and so I have 2 times tangent of pi over 4 is 1. Secant squared of pi over 4 is 1 over cosine squared pi over 4. Cosine squared of pi over 4, or I'm sorry, cosine of pi over 4 is the square root of 2 over 2. If I square that, I get 2 over 4, which is 1/2. But secant is 1 over cosine, so it's 1 over 1/2, and so that's 2. All right, so we have 4 as our slope. So now we have a slope and we have a point, and so we can simply put the two together and say, okay, using our point slope form, then we have y minus 1 is equal to 4 times x minus pi over 4, the end. Okay, and that's as far as I take it. It asked for an equation. It did not ask for the slope-intercept form of the equation, and so I don't see any particular reason to give them that much. Okay, I have been warning my class, and your instructor has probably been warning you if he or she hasn't already given you some of these word problems. And so here's a goodie. The speed S of blood that is r centimeters from the center of an artery is given by S is equal to C times the quantity capital R squared minus R squared, where C is a constant and C has a value of 1.76 times 10 to the 5th. The capital R is the radius of the artery. S is measured in centimeters per second. Suppose a drug is administered and the artery begins to dilate at a rate of dr dt. And so the capital R is changing with respect to time. Okay, at a constant distance r. So remember, little r is constant. That's kind of important. He's constant. Find the rate at which S changes with respect to t. Okay, so we need to find ds dt. All right, now our chain rule says that ds dt is the same as ds, and now r is changing with respect to t, and so that's a variable, d capital R times d capital R dt. All right. Now earlier we had df or or dy, either one, dy dt is equal to dy over du times du over dt, or du dx. So here we go. We have a nested function. Okay, this is actually a function. And so when we take its derivative, we are actually looking at r of t. That is squared. Here we go. ds dt is equal to the derivative of s with respect to r. The only variable in this thing is capital R. And so this is really c, the constant, times the derivative of r squared, which is 2 capital R. Okay, that's where the ds dr comes from. And now we need to multiply that by dr dt. Okay, and so our second part comes from that. So this thing is actually r of t, which means we need to take the derivative of it. So it's take the derivative of the outside, which is r squared, which is 2r, times the derivative of the inside, which is r prime of t. So now ds dt is actually equal to 2c times capital R times the rate, dr dt. This is what I meant earlier when I kind of hinted to it, that there's a secondary rate here. So ds is changing according to the radius, the speed of the blood is changing according to how the radius changes. Okay, so there's two things changing, one dependent on the other. And that's what this is really kind of nice for. We have C and R. C and R are 1.76 times 10 to the fifth and 1.2 times 10 to the negative 2 respectively. And so let's go ahead and bring out our handy dandy calculator and see if we can't calculate this. Okay, and when we take 2 times C times R, all right, let me change colors again here, kind of bring this down. We have 2 times C, which is 1.76 times 10 to the fifth, times R, which is 1.2 times 10 to the negative 2. This thing is equal to 2 times 2.96, 0.96 times 10 to the 3, which this is 4 less than 3, so it's going to be 8 less than 6. And so this is going to be 5.92 times 10 to the third. But we still have to multiply that by dr dt. And so we have ds dt is equal to 5.92 times 10 to the third times 1 times 10 to the negative 5. And I got that value from here. And so if we do that, then we simply multiply the 1 and the 5.2 or 5.92. And so ds dt is equal to 5.92 with the other 2, kind of the 2 that looks like a 2, times 10 to the third times 10 to the negative 5. You add the 2, and so 10 minus, or 10 to the third times 10 to the negative 5. You're multiplying two things with the same base, so you add their exponents. 3 plus a negative 5 is a negative 2. And so the speed at which the blood is traveling at is 5.92 times 10 to the negative 2 centimeters per second. It's not moving very fast, but fast enough to get our blood pumping, so we're happy. Remember, this involved the chain rule, and rather than use the informal definition, which I've been using quite a bit with, I went back to the more formal look of this ds dt is equal to ds dr times dr dt. And a lot of that is determined by the fact that I'm given one of the rates.